the major informations about the major differences of the analysis of the course. Then CMSIS, a few things about the CMSIS and what's this, what are the major elements, how to use the CMSIS in practice, and why to use the CMSIS at all, where to find the documentation about it, and last but not least, analysis of the existing microcontroller families based on the STM, on the cortex core. So a couple of examples only, of course, because we have currently in the market there are so many various cortex microcontrollers, so that it's useless to analyze everything and to even get close to this. So on some examples only, this market analysis. So that's the plan. That's the plan for today. Previously, we began with the cortex and family, and with the course we finished with the last core that is still available on the market. That is available on the market. So the new course dated, so Cortex M23 and Cortex M33. So the newest breed, of course, described in the 8 description, 8 version of the architecture, of the ARM architecture. So ARM v8-M. As I mentioned last time, the M23 is a simple core, so it is something slightly better than 0+, but with the security, with the trust zone being added to the core. So this is the major difference here in case of Cortex 23. In case of Cortex 23, in case of Cortex 33, so again, the very new. It's the first hardware I saw about a year, maybe about 2 years ago, something in this time frame. So it's pretty new, maybe not very new, but pretty new. The description is about a year older. So 33 is something about M4. So it's not really faster than M4. So it's at the same level of M4 in case of performance, in case of peripherals. So we've got the again the DSP and the FPU coprocessors here available. So like in the M4, the new thing is the coprocessor interface, meaning that the manufacturers of M33 can fairly easily add their own instructions to the instruction list. So this is an improvement over the M4 core. Additionally, of course, there is the trust zone, because the common feature of the M33 is a trust zone. Theoretically, it has slightly better performance calculated with the core mark. In case of dry stone, the performance hasn't changed, or is even slightly worse than in case of M4. So all in all, it's very similar core. So all in all, slightly better features, but similar core. And M33 is there, so there are some hardware units already available with 33 core on the market, like with the 23. The next 2 cores that are so the last one that are available, because up to my knowledge there is nothing newer, are the 35P and the 55. So in case of 35P, the difference is adding another protection layer. So it is called anti-tampering. In case of the trust zone, this trust zone especially works especially well. So there is one lecture planned about the security features during the semester. So I will try to tell you more about it. in the second part of the semester. I'll try to tell more about it, but in general, the trust zone is especially good when protecting against remote access to devices. So we've got secure elements of our code, and we've got non-secure elements, and then with the trust zone protects the secure zone against remote access, especially. Still, it turned out that it's possible to, with the use of a fairly simple tools, hardware tools, to get an access to a microcontroller with the trust zone protecting layer. It's possible to get the access here just by reading back or back engineering or reverse engineering of the password. That's protecting the trust zone. So the M35B is the response to this problem. So it's protecting the access to the trust zone. More or less, it's about this. So just in brief, still no major manufacturer is delivering the M35P to the market. So it's still pretty new solution. I'm still waiting for any hardware to appear that would utilize this in practice of this M35 and 35B. Much more interesting from practical point of view is 55. It's very promising controller. So this is something between M4 and M7, looking from the performance point of view. So it's sharing some features with those two processors, especially with the M7. So, for example, we've got this tightly coupled memory. We've got the cache both for data and for instructions. Of course, this is the new breed, which means that there is a trust zone as well. So the protection mechanism are there. The core itself is not super scalar. So the core itself reminds very much about the M4 core. So the FPU and DSP extensions. Yet, what's the most interesting here actually is the Helium unit. Helium, which is a vector unit, for speeding up the vector operation. So generally, it's the SIMD. In other words, is the SIMD unit. The SIMD unit, which is giving a boost in the performance where the signal processing and especially machine learning is used. So this is the processor for artificial intelligence. It will be, because still there are missing. I haven't seen any units thus far on the market, although I've been searching. I'm waiting eagerly to get my hands on this kind of unit. As I'm waiting since some time already. I've been waiting. So AI capable processor. Theoretically, the basic performance of the core itself is not extremely fast. So this is something only a tad faster, a tad more efficient than the Cortex M4. So this is not extremely fast, but for the SIMD operations, so the vector, two names for actually the same. For the vector operations, at least that's something that the ARM is promising, that the processor should be very, very fast. Should be very, very fast in case of these vector operations. So therefore, the signal processing and the AI applications might make use of this. Might make use of this performance. So we have to take a look at this chart. So of course it's theoretical. Of course, it needs to be tested in real conditions. Is it really gonna be this nice? Because it's a bit surprising, at least for me, these values. For the 8-bit operations, 6.5 times faster than M7 theoretically. With M7 super scalar core, here vector, operations, because we talk about this Helium coprocessor. Still, with 16-bit and 32-bit fixed point, it's just, let's say, just 3 times faster, but it's still a huge performance difference. But what would you say about floating point with half precision? So of course we're using half precision pretty rarely, but still the floating point with single precision, they promise to have it. The processor should have 3 times better performance comparing to the existing M7 solution. Yeah, the M7 was up to 2 times faster, if you remember last week, and this is really the case. So the M7 is really about twice as fast comparing to M4 because of the TCM and cache RAM available, and because of the superscalar pipeline and superscalar in order. Okay, but it's still a multiple execution unit, so with proper optimization of the code, doubling the performance of M4 is possible for M7. Yeah, but what would you say about making the performance multiple times faster? Naturally, it's only about the calculations. It all results from the SIMD of the Helium SIMD configuration, so the parallel operations on data. So it means that for the applications, it would be this way only for the applications requiring processing of a lot of data, large amounts of data in the same way. So video probably, maybe even video would be possible to process with this kind of processor. We will see. So still I'm waiting for any hardware. In the meantime, though, I think that it's worth mentioning. Yeah, so there is from Jakub. There is a note about the Intel making the AVX 512 and having it power hungry. Yes, of course, that's the good question. If we put too many resources and if we start clocking it too high, then there is physics, pure physics, and more transistors clocked at higher frequency require more processing power. Naturally, we have a certain defense against this excessive processing power with higher technology nodes. So the larger cortex M's are today being very often produced even with at 28 nanometer technology node, still far from this technology node of the Cortex A processors, because they are today they go below 10 nanometers. We'll see how it goes in the future. So the Cortex, this Helium is something that's really needs testing, because it's very promising. It's very promising today when we talk about machine learning very extensively and about processing video pictures or in general the data, the matrix data coming from camera, which require this vector processing actually very much, and because we want the customers require more and more often analysis of complex pictures and the fusion of sensors as well, coming from fusion of different signals coming from various cameras. So the Helium is an interesting direction about increasing the performance of the microcontrollers. Second direction of increasing the performance of the microcontrollers is including in the design of the microcontroller the A cores. They are since years there were available microcontrollers based on Cortex A5 core, which is a single core, which is a very simplified Cortex A core, so cut to the bone, so I would say, the A5. But recently, quite often, so I saw in a few applications, and as well the ST is has this core in the market. So this is the A7. The A7, and what is the cortex A7 core? So the A7 with combination with the standard M4. So this is another method of increasing the performance. You know, so the path with helium. So there is this M7, which is basically a simplified, or the cortex R7 translated to microcontrollers. Then to single core applications. Then we've got the helium, which is something new and something that, as Jakub mentioned, is appearing already. So in some applications, but it's still not in the wide market, in the broad market available. But it will appear, definitely. It will appear on the market. It's just a matter of months. That interesting units, hardware units, will be there with this Cortex M55. Yeah, and then we've got this third path with the multiprocessing, with multi-cores, with asymmetric multiprocessing, because we talk here about the architectures where we have two completely different cores doing different jobs, yet sharing some peripherals. Most of the peripherals are being shared. Only some peripherals are dedicated to certain cores. I will show you an example, physical example of the MP1. Because this is the family. I mean, but it's not only ST that is doing this kind of course in physically. So A7 is generally the core that's supporting multi-core processing. So theoretically, in case of the A7 core, it's possible to have it in multiple cores, but multiple cores this time working symmetrically. So again, we'll get back to this multiprocessing during one of the lectures, probably this semester. Just to make it short at this moment, it's possible to have multiple core solutions. Still, it's not available in microcontrollers. So when we have a microcontroller, then the units I saw are just single core. Second core is M-type core. The important advantage of the Cortex A core in practice is the virtualization possibility. So the physical address can be up to 40-bit, and so 32-bit is the addressing space, but there's a virtual addressing, and so in general, formally, we've got memory management unit of virtual memory system architecture here applied, which means that we can, on this Cortex A7, we can not only set up a real-time operating system, so some simple RTOS, but we can also try to start here fully operational GPOS, so like a Linux. So this is possible because we've got virtualization here. So we can try to set up a GPOS as well. This Cortex A7 is supporting SDRAM memory because it's the processor. It's a simple but still application processor, which means that it's natural support for gigabytes of SDRAM being connected here, and such an interface is also available, usually made available in physical hardware units, so that we can really set up here operating system on this processor, fully fledged, so Linux operating system, where the side core, because we talk here about the A7 working in comparison with A4, usually M4, yeah, because I have not seen a combination with M7, which would be interesting. But anyway, the second core then takes care about the hardware, about the communication, and with various peripherals and this kind of stuff. In case of A7, as I mentioned, 4 cores available with SMP technology. It's about 20–30% more efficient in single core, at least theoretically, than A5. It's difficult to say, so at least so far I failed in comparison. So right now I'm waiting for one of diploma student to make a comparison during his diploma, because that's his job, about the performance, real performance of A7 and M7, and make the comparisons of how faster or slower the single core A7 is comparing to M7. Physically, it is faster usually because it can run up to 1.6 gigahertz. I saw such numbers, which is pretty fast. Although the MP1, the ST version of the Cortex A7 is just 800 megahertz clocked. So it's still pretty fast. Important in case of A7 comparing to other A microcontrollers is the power consumption. With microcontrollers, we like very much to have low power consumption. Here we talk about less than 100 milliwatt for the core itself at running at giga plus, so around 1.2, 1.4 gigahertz. Still, they promise that, so the ARM promises that at 28 nanometer technology node, for example, it should have less than 100 milliwatt, and then at lower technology node, it shall be even better than this value. So 100 milliwatt for a core itself, it's just a nice value. Naturally, far from the values that pretty far from the values that we were talking about. We're talking about at when analyzing Cortex M0, M0 Plus, what this were microamps per megahertz. Here it's 100 microamp per megahertz, but still it's fantastic. Still it's fantastic. So this core can be used, taking into account that we've got of course DSP extensions, we've got vector floating point unit, and we've got the SIMD unit on board. So again, it would be interesting really to compare it against M7 and as well against Helium. So how much it will add up, or how much is it better or worse, because I haven't seen such a comparison thus far. So again, that's something I'm monitoring, so I'm trying to find, but thus far nobody shared at least such a comparison, especially with the new M55, how much, so against M7 and M55, how much it stands still. The A7, the major difference that will be there, because in M microcontrollers we don't have the virtualization support. So we are missing in M basically the SMP technology and virtualization support. That's missing, and it's not in plans. Which means that if you want multiple core and if you want operating system full operating system, so GPOS, you have to go A7. In all the other cases, in case of performance, the M7s and the M55s are so promising that I'm really waiting for the comparisons. Maybe when we talk after this semester sometime, maybe I will have the results, and maybe I will share. Maybe we'll talk about it. That's it about the hardware that we have in microcontrollers, so that we have implemented in various hardware units. So these are, of course, just the cores. It's even getting more interesting when we get to some hardware units. But before we start a brief analysis of the hardware units, I stop over with the software. With the software, because one of the elements that are responsible, let's say, for the success of Cortex M architecture is the Cortex, the Cortex microcontroller software interface standard. So it means that not only the cores, so the ISA, so instruction set architecture, has been standardized or is standardized by the ARM, but also they did standardize the software interface. So the software interface to the microcontroller. So what is in general the CMSIS? In general, thanks to this, so this is just a framework. Framework with a lot of different blocks, supporting the software development on the Cortex platform. This CMSIS enables formally consistent device support to processor and its peripherals. Consistent, so that it means that we can change the platform, and still our code will be relocatable. So we can easily recompile the code, because what we need to change, it's not always so simple, but it really works this way. So if at certain level, if at the highest level we start to use the procedures, then we can jump from platform to platform, of course, having Cortex microcontrollers, and our code should work, should follow these jumps, should follow this changes of platform. So just recompilation then is necessary, but the code itself keeps same. The code itself keeps same, and not only that's the beauty of it. That not only we can change within the family. So not only we go from STM32L0 to STM32H7 something, but also we can switch between manufacturers of the processors, with certain disadvantages, certain differences in case of peripherals, because if we try to use the feature of a peripheral that is available only in Texas Instruments implementations, naturally it won't be automatically translated by the CMSIS to the NXP version of the hardware. But the major hardware, the simple hardware, like the SPI, UART peripherals, like memory accessing, of course, the core itself, all this is very neatly and very nicely translated automatically, or taken care of automatically by the CMSIS and by the procedures inside the CMSIS. So the major idea and the major advantage of the CMSIS is that thanks to this fact, we've got that the code can be located, can be moved between the platforms easily. We've got the simple software reuse. We've got reduced learning curve, and thanks to the reducing of the learning curve and simple software reuse, our time to market is reduced. Time to market is reduced, and that's what matters. So lower time to market, more money. Of course, the money is the issue here. How does it look inside the CMSIS? How is it standardized? So naturally, at the bottom, we've got the hardware. So this is the gray one, the gray thing. So we've got the core itself, we've got the peripherals of the core, we've got other peripherals, and we've got the core side, which is the debugging part, with all the debugging elements, hardware elements, because we talk here about the MTB, about the ITM, about the ETM, about connecting through JTAG, because SWD block, JTAG block, so all these elements, so there are plenty of such elements inside the microcontrollers. And again, we'll get back to this when the time comes. Naturally, physically, the largest block usually in microcontroller is, of course, the other peripherals, because here, so don't get misled here. The other peripherals is not just that it's one or two peripherals, because usually the core peripherals are like the SysTick timer NV, and that's it, and maybe SAL. But other peripherals, because debug and tracing could be classified even to the core side, because these are the debug peripherals. But in case of other peripherals, we've got 5 UART, 3 SPIs, the 2 ADCs, 1 DAC, Ethernet, USB, CAN, 10 timers or 17 timers. So that's what is meant by other peripherals. Here. Then on top of it, we've got the first layer of the model, where so this is called the core. This is called a CMSIS core peripheral. The CMSIS core is delivering the abstraction layer. Is delivering the abstraction layer here it is written, is delivering the so-called hardware abstraction layers. That's what the CMSIS core is being delivering, which means that from this core version, from the core itself, when using the methods which are hidden in the libraries, which are hidden in the core itself, we are losing the register, the direct access to registers. So we still have access, of course, to the peripherals and to some registers, but with the core, the position, for example, of bits in the registers is obscure. So we stop writing to assigning to registers a certain value, so like FF15, but we start assigning to the registers, accessing the bits in the registers by the names. As well, we don't access the registers by their address, but we start using the names of the registers, which makes this is the first step to make the code relocatable, because then the manufacturers, of course, each manufacturer may have different addresses of the UART block, of configuration registers, and so on. So all this is taken care of by the CMSIS, CMSIS core block. Yeah, by the way, the CMSIS core delivers the API and provides the standardized interface. For over today, it's more than 4,000 different devices, hardware devices. 4,000 by that. So that's why the reason. That's one of the reasons that CMSIS is such a huge number of devices, of cortex devices available. So that's the reason. The CMSIS has a sense, because the cortex, especially, so that we that we can have the intermediate layers of which takes care about variants of the devices. So going further, we've got the next. So first we have got the hardware abstraction layer. So we have standardized names of the registers, we have standardized names of the bits, and we are accessing the registers with the use of the name, by the names, not by the bits itself. As well, the exception names are having the standardized names. So the table in the interrupt table, everything is present. So we've got the startup file as well, with some basic operations already predefined. So that's about the CMSIS core. Additionally, no, I forget about it. Additionally, we've got the some methods already, of organization of header files. So it's there. So we've got because the header files consists of definitions, so they have all the definitions inside, and with the CMSIS there is a certain method with the certain naming convention, so that the header file, so that you read the name of the header file and you see which family of the processors is described in the particular header file. Then we have the system initialization, standardized a bit as well, and we've got some intrinsic functions which are automatically generating some non-C supported instructions, because there are some instructions for various operations, like enabling interrupts, for example, which are assembly instructions and which are not present in C. So these intrinsic functions that are there present in the CN, or are delivered by the CMSIS core. Then on top of this, on top of this core, we've got, going back to the model, on top of this, we've got the libraries with the libraries with so-called hardware abstraction layer. delivering us the device specific access to the device. So usually it's so neatly integrated with CMSIS core that we don't pay any attention that there is a special hull, because the hull is device specific, and it's this is just the framework, so the core itself, and hull. So the hardware abstraction layer is the content with the so there is a system, for example, of the includes, and the hull itself means that we have a content of this include. So the details are present in the hull, in the hardware abstraction layer. Then we've got as well here, going analyzing blocks by blocks. We've got the kernel of the real-time operating system, because the CMSIS itself, in the CMSIS we have described the API for the RTOS, a standardized API, but we can use different RTOSes. So there are a couple of them on the market. So FreeRTOS, Azure, for example, from Microsoft. So there are a couple of various others. There are a couple of RTOSes on the market, and with the CMSIS, we can blend them into our code and use standard API delivered by the operating system. Then we've got this part, so the middleware with the driver, sometimes delivered as well. That's using the lower level access functions delivered by the core plus hull to form some predefined functions, so predefined elements for this, cutting out completely or almost completely our application code from the hardware. So for example, if here at this level we have functions, low level functions accessing particular registers. So instead of writing to registers, we've got function, because at this level we've got accessing of registers, if not writing a single bit, but using some naming conventions, but still we've got some simple functions modifying registers in a peripheral, for example changing the baud rate of the peripheral, of the UART or SPI, whatever you are configuring. That then at this level we've got functions for initializing the whole peripheral. Functions accepting which accept a structure, and in this structure first we need to fill in the structure, deciding which peripheral, in what way, with what optionality is to be configured, and then this function is using the lower level functions, so the functions from this level, but our application code doesn't see at all the bit and registers, the bits and registers, which are still seen at this level of abstraction. But additionally to this, very interesting are those libraries. So the DSPs, DSP and neural network libraries, because they are in case of the CMSIS, these are libraries supporting heavy math calculations, and delivering us a great deal of methods. So these libraries, as you can see on the model, they are not using the HAL, neither HAL nor the CMSIS drivers. So they are, because they really usually get down to the core, maybe to some memory, so they don't care about other peripherals, because that's what the device HAL is doing, is giving access to everything hidden here in the other peripherals. In case of the DSP and neural network libraries, these are the usually purely mathematical libraries optimized for particular core, because they exist in different for different core. We have different libraries that we need to add. delivering us the method and the structures, various methods and structures, starting from basic math, but going through complex math functions, for example, filters, matrix functions, transforms, various kind of motor control functions, statistical support, interpolation. So no, it seems as if somebody installed a MATLAB on our microcontroller. It's not that simple, but in reality, we've got, take a look at what the matrix functions example we have available. So first of all, we've got the matrix structure. Remember, in C, we have table, we have an array, we have a structure, we have an array. In C++, we can have a class and methods to this class, but that's it. But we don't have a matrix unless we do the matrix and we construct the matrix. Yeah, we can make a class and construct the matrix class and construct the methods, add the methods to the class, but this will be done on the C level with the use of CMSIS DSP libraries. We have this done at the assembly level, optimized for particular core. So you take M0, you take M4, you take M7 libraries compatible with particular cores, and you get the efficiency. Again, you can do it with classes. You will have your code relocatable completely between even different platforms, between Atmel and Cortex, for example, platform. With the use of CMSIS DSP, you will have it relocatable just within the Cortex family, but hey, 4,000 different chips available on the market, so plenty to choose from. But this is very optimal. So I tested a couple of functions here from this CMSIS DSP libraries, and they do the job. Really, they do the job. So C code is not optimized to such an extent. It's not as fast and as efficient as the functions available in these libraries. And as well, the same is for the the same is where's that neural network? Yeah, the same is about the neural network. So the NN collection is the collection of the functions or procedures efficient in the kernels. So the basic neural network functions are there, like convolutions, like pooling, like activation tables. So you can try to use a TensorFlow, and from there you can try to optimize TensorFlow Lite, because that's what's available here. You can try to make the TensorFlow Lite, for example, and implement a neural network pretty directly into CMSIS, and then with the use of CMSIS neural network component. So as well, an optimized version of neural network, optimized for particular platforms. Some examples based on Kyle and on ARM documentations already after a break. So let's have a short break and we'll get back to this after the break. Okay, welcome to the break. So DSP neural networks are just very interesting library. So I'll show you how to use them in a moment. Just to add one more thing, because we talked about the middleware, about the organ. So here about the middleware software. As you can see here, as added by the third party as well, something quite nice and quite interesting, especially in case of some advanced applications like USB, like TCP/IP, like the support for graphics, for the file system. All this is added by middleware, partly supported as well by the manufacturer, so it has to be supported. But in general, it looks, as you can see, like this one, the structure. Middleware, then the middleware uses the devices, the drivers available in the device packs, and only then we've got the access to the hardware through the core. What is left from from the the components exist before the debug part. The components that exist in case of CMSIS are gathered in so-called packs. CMSIS packs. They give the access to the software components. There are various packs available from various directions. And for example, the major packs are the DFP, so device family packs, where the important vendor-specific files are available. This device family packs tends to be pretty heavy physically, so we talk about hundreds of megabytes per family. By family, I mean for example, the F4 that you're using on the lab, and it's 300, 400 megabytes, and each family is more or less this heavy in case of family pack. Then there is with the CMSIS installed the software pack with the core DSP. It's in the software pack. There is a middleware pack as well. So all the packs are available. The elements of the CMSIS are available in packs, and we have to download the various packs depending on our needs. Sometimes we have to do it by ourselves, so sometimes it's not completely automatic. Although the various softwares working with CMSIS that usually do the job. Additionally to the standard components, we've got two components useful in debugging, so the SVD and DAP component. So the SVD is a component with delivering a view to the device and peripherals. From the debugger perspective, the files for SVD are maintained by silicon vendors, so it depends pretty much on them. The DAP on the other side is the interface to the physical DAP inside so the back access port inside the hardware microcontroller, and from there we've got the access to particular core sites in particular cores. We'll talk about it as well when we analyze during the lecture, when we analyze the debugging capabilities and how the debug is working in general in various microcontrollers. Before we go into some basic market view, I would like to show you how to use the CMSIS in practice. What is special? What are the options that we actually have? Yes, to do this, I need to share another application. So namely, let's start with Kyle. In case of Kyle, the basic core mechanism is here. So the basic core mechanism of CMSIS core. By CMSIS core, it is meant that we have this type of access, that we've got the include file, we've got the startup file, so you should know it from the lab already. So we've got the include file. So here is the include file. The include file delivered by the in the appropriate packs. In this input file, in this startup file, we've got in this include file, we've got the device, the particular device, because that's what is meant by the structure in case of CMSIS, and we've got the particular device include file. So again, in one family we've got many devices, and then all the definitions are here. So the definitions in this include file, the definitions, if there is a peripheral, this works this way, that if there is a between the various microcontrollers, if there's a peripheral sharing the functionality, but not really sharing the positions of the placement of the bits, then still, if we use this these definitions of the bits, so the convention is that the group, the register, and the name of the bit that you take from the documentation, then still everything will work. Still your software should be relocatable, so should be reusable on different platforms. It's not all that funny, unfortunately. So in real life, switching from between different micro controllers, it's not that automatic even if you use CMSIS, but it's much easier. I must admit that it's much easier, much easier than when playing just with values, just with the registers. So this is the use of this kind of notation that comes from CMSIS core itself is pretty much advisable in practical applications. So this is the level of CMSIS core. Then, if you want to use more, in case of CMSIS, then we go to the runtime environment. And first of all, we've got the CMSIS driver. So the CMSIS driver in the structure delivers are some methods that we can use in our devices. We can then add to our project the CMSIS driver. It requires some additional. It writes here in case of cube. It writes what should be added additionally to our so device cube HAL common. We should add here. But what is most important, what I wanted to show you are the methods. To see this, because if you click here, you get a web page opens. Now you should see at the Internet Explorer with the documentation for the CMSIS driver, because here in this documentation you can see the methods you get from higher level. So this time at this level, at the level of the core, not core but the driver, we are not just assigning values or bits to some registers, but here we are rather using methods. We are rather using CMSIS methods, the driver methods, which are standard. So the idea of using these methods is to avoid, is to write a code which will live not only in our device, but that will be relocatable to other devices. And for example, we've got a method for initializing the SPI. Well, we just fill this structure. So ARM SPI, signal, even T, whatever the structure is. We point out this structure, and then we call the method ARM SPI initialize. In this structure, so of course we can check the structure. We've got various information about the SPI configurations required that we need to fill in order for proper configuration. Take a look. It cuts us out completely. It takes us out completely from the use of these structures and the use of this method. It takes us out completely from how is it done, because it differs from even within ST. We've got SPI blocks, so the older ones and the newer ones. In the older processors and the newer processors, we've got, for example, to give you one small difference. In older SPIs, sending data over SPI required writing something to data register, so to DR. In the newer SPIs, we prepare the data, and then we set up a flag that starts the data transfer. Then we can transfer more data than just one data at once, and we don't always need to use DMA for sending more data. And the reason of using these methods from the CMSIS driver level is actually to avoid the problem of which bit should be set for starting the data in this processor, and which bit should be set in starting the data in another processor. So then we just simply use the ARM SPI send method with pointing the amount of data, pointing the number of data, and it's done automatically. So again, back to our structure. We talk about, I mean this level. So take a look. That's let me clean it up a bit. I mean about exactly this level. What was before was the CMSIS core level with the register. So it's a bit different level. We've got also the HAL level, hardware abstraction level, which as well we can use, but it's more vendor specific. So the problem with HAL level is that we've got the functions which they're available at the ST, for example. If you're using the STM32s only, then you can use then your code will be reusable between different STMs. But if you change your project, if you intend to write something that will be universal between the STM32s and NXPs and Texas Instruments and analog devices, because it's possible as well, then staying at the HAL level, it's a bit problematic, because of course it's not going to be the same at the NXP platform or Texas Instruments platform. But using this CMSIS driver method, so the method shown here guarantees us that it's going to be relocatable. So that's really fabulous. That's really nice in case of the use of that. That's really the advantage when we are using the cube, the CMSIS. Another thing about using CMSIS, because this is about the using of drivers. So yeah, we have to add the drivers, and they will be automatically includes will be automatically added, and the package is downloaded if necessary. Another interesting feature is the use of these libraries, exactly. So the DSP and the NN library, neural network library. And again, if we so adding them is so simple, but they are described in here. So they are described in this. They are described here in the CMSIS DSP web page. This time CMSIS DSP or CMSIS neural network. So you can see here as well at the top the packs described, and here you can see as well how many different libraries there are for each cortex line. So we've got the libraries that are dedicated for M7 with little endian, with double precision floating point unit. So if in the processor that you are using it's a double precision floating point unit hardware, double precision FPU, then you have to point this library, otherwise single precision. We've got the M7 standard with little and big endian with software only, without the FPU, as well with M4 with floating point unit with software support. You can choose. If we have the FPU, hardware FPU, there is no sense of using software calculations, but you can do this. We've got M3 optimized libraries at 0, and then we've got the libraries for the ARM version 8. So these are the new microcontrollers. So the Cortex new core, so M23, 33. So 23 is the baseline. So this is the library for this baseline version. The main line is the 33 and up. So 33, 35p and 50, 55p. And then we've got all the goodies that we have here. So we've got the data structure. So take a look how many data structures we have available for various precisions. So here Q15 means 16-bit precision, Q31 means 32-bit integer precision, F32 means single precision single precision float, and then we've got the functions. Even simple functions there are, like negation, absolute value addition. So all this is optimized. So instead of adding, take a look, instead of adding writing the your own procedure, because we can do this in by using C code and writing a simple loop, adding the 16-bit numbers, integer 16-bit numbers together. Yeah, so C writing, so destination equals to source A plus source B, so and looping it of block size, so this many numbers. Yet this method, very simple, still would do better. So, okay, you can write, take a look, you can use this method for adding together multiple blocks, but and you can try to write it by yourself. This method has the advantage, that yeah, it may work similar in the processors not supporting vector operations, but if you recompile your code to Cortex M7 or M55 supporting the vector operations, then your code will just fly in case of performance with the use of this method. So take a look, even simple 8-bit method is available for adding together two vectors of data of any size. Still, this is optimized, and not mentioning not mentioning the functions which are more complex, like integer cosinus. Take a look, not floating, because there is a floating version, but there's also the fractional version of the cosinus, and the functions like the various complex functions, complete math functions, matrix functions as well. So of course we need first to prepare the structure, so it's not as simple as in MATLAB, but much simpler than everything done by ourselves, and optimized, of course, for a particular course. In case of neural networks as well, we've got a lot of functions which go together with the construction of the neural network. So you can design a neural network in some other software, take the structure of this neural network, and then implement all necessary functions here directly in the microcontroller with the use of neural network libraries, so CMSIS neural network library that you have here. So briefly, it looks this way. So the CMSIS is really worth using. At different levels, we can use it, really at different levels, but even if you, it's really worth using it during our everyday programming. It gives us a huge improvement in case of time to market, so reduction of time to market improvement, huge reduction of the time necessary in development of our devices. Still, don't forget about one important thing, that even if you try to use the CMSIS at the level of middleware and or at the level of the CMSIS driver, still you must understand the microcontroller peripheral, how they work and what can you get from them, and what is more or less necessary for configuration. So even if you use a method which hide this complexity, which hide this configuration, the bits and the registers, from my experience, there are no shortcuts here. So still, during the debugging, still there's a good chance that something goes wrong at some point, and then you'll have to get back to the debugging of the bits and the registers. Because even if you use these high-level functions for example, configurations and the usage of SPI, then if something goes wrong, then the view will show you just the registers and the bits itself. So the CMSIS libraries are excellent for making the code reusable, are excellent for making the making the time to market shorter of your project, but they are not replacing the need to know how the processor is working, the need to know how the peripherals are constructed, constructed, and they need to know at least the major registers in the peripherals and the major configuration operation of the particular peripheral. So it's not that simple. It's not that simple. It's simpler, it's better, it's really worth using, but it's not replacing this basic knowledge. Don't forget about it. Good, and we go to the last part of today's lecture. So the short market view, a brief market view. So I already mentioned there are even more than 4,000 devices, or around 4,000 different hardware devices, including the Cortex microcontroller. So huge number, really huge number, and a fabulous choice from an engineer point of view. So we can choose the device that we need, really, and then we want. So we, of course, will not try to analyze completely every possibility. So it's useless, it's futile, as there are so many, but rather the category. So we can classify the Cortex microcontrollers today into those four major categories. So the category of the high performance core, so the fast, sometimes even dual core solution. So we have the here in this classification today mainly the F4, F7, H7, so dual core M7 and A7 solutions, because we can put here in this family as well the A7 plus the M4 solutions for the high performance. So this highest performance, naturally, usually the neural networks or artificial intelligence, graphics, various graphical user interface or matrix sensors. So the cameras, because that's what requires such a high processing power. A bit about the motor control here as well. Sometimes we need this high performance in this kind of applications. Then we've got the mainstream applications, the mainstream processors, where there is a balance between the very high processing power and huge number of peripherals, and the low cost, low price, and low area. So small cases. So there is always some kind of a trade-off here in this kind of mainstreams. Usually about the mainstreams we talk with the cores of the starting with M0, but clocked at with the high clock rate M0. So take a look here. We've got in this mainstream. So in this example, we talk about even 64 megahertz M0s with the families of G0, M0. So highly clocked M0s here, then M3s, because the M3 is the general purpose family, the mainstream. So we have the M3s are usually clocked up to 100 megahertz. So it's pretty rare view to see M3 clocked higher. Usually M3s are clocked between 20 and 80 megahertz, or somewhere in between. Because if somebody needs a high performance processor, then simply we switch from the mainstream to high performance. And then we've got here somebody put here the 170 M4, which I would place in fact here. The M3 for me is rather the mainstream, because don't forget the M3 is missing both the DSP instructions and the FPU unit on board, which makes, so today, from today's perspective, the M3 cannot be classified as high performance, even if it is 120 megahertz. Then we've got the ultra low power category, ultra low power with the processors, especially the Cortex M0 and M0 Plus, clocked at low frequency, as well Cortex M0 here, clocked at low frequency. So this is what I mean, what is meant by ultra low power. Take a look here. It's placed the M33 with 110 megahertz with 442 core marks as well, and some basic M4 with L4 plus category, but then it's just low power. So ultra low power is never 100 it's never 100 megahertz plus. So we talk about really 20 megahertz or lower. Although of course you don't need to utilize, you don't need to use the highest clocking available. So you can just switch on the highest clock for short time and then switch it back to some basic clock rate, some like 8, 10 or 20 megahertz. Still here in this, in case of this ultra low power, we've got usually, so here we should classify M0s, M0 plus and M23s. So the cores with the processor with this cores we can classify as ultra low power. And then we've got category number 4 with the wireless cores, especially important, so very important category today, category that is as well pretty much growing because of the IoT applications, so all these Internet of Things, so that we want our embedded system to be visible in the network, to merge with the network around, so with Wi-Fi, with Bluetooth, with Thread as well, so the wireless sensors, mesh of sensors, something that the customers want to pay for, so we should be able to deliver this kind of application. So that's why the wireless families are getting stronger and stronger, especially because it turned out that the M0 and M0 Plus cores are so small and so power efficient, then it's really worth including them as a sole coprocessor, a sole wireless coprocessor. And that's the reason why we have today, for example, in STM, the family WB and as well family WL, because this slide was taken some time ago. So today they are dual cores, STM32WLs and WBs, with the major core being M4 and a supplementary coprocessor, wireless coprocessing core being the M0 Plus. So then this coprocessing core takes care about the protocol complexity and about the network complexity that requires quite a lot of effort. So with single core, then the core is loaded with these tasks, and with dual core solutions, we've got the major core free for all the other operations. So of course 64 or 48 megahertz cortex M4 is not extremely fast, but still it's still M4 core, so still pretty nice solutions. This has to be low power. That's why the wireless are usually not extremely fast clocked. So take a look, 4 major categories. Whichever producer, whichever vendor of the silicon we take, they produce. We can try to classify the processors they do produce into those 4 bins. Sometimes there is a 5th bin of automotive. Yet the automotive is just meeting special criteria, but in case of performance and features, they can be classified within those 4 categories. So high performance, mainstream, low power, ultra low power, and wireless functionality. That's how it is. In case of the peripherals, because we have so many different microcontrollers, then we also have some subfamilies, and then again each manufacturer has its own idea how to do this. In case of STM, we've got families with F letters, so STM32F 0, 1, 2, 3, 4, and 7. Then we've got the L, so L0, 1, 2, 3, 4, 5. Then we've got W for wireless. We've got G for general purpose. So the new, and MP1. So now it's the newest is the MP1. They vary not only because of the cores, but they also vary because of the peripherals. So the number of peripherals, the quality of peripherals. Yet naturally, if we have a wireless SOW version or in general wireless, there must be some wireless peripheral. If we have an ultra low power, then the number of peripherals is reduced. The core may be left larger, faster, but the amount of memory and the number of options in case of peripherals must be lower in order to get lower power consumption as well. So I think it's quite natural. And some examples to show you what you can expect from particular families. So first of all, the low-cost family, low-cost, low-power family, so the L0. And what's in this L0? What's in this kind of smallest ultra-low power processor? So the core itself, low-cost, low-power, low-speed, unfortunately, core. So we talk here about the M0 Plus only, with only MER 32 megahertz. So this is faster than the cortex, than the ARM or microchip 8-bit constructions, as well with 16-bit microchip constructions are weaker than this, because we talk about simplified 32-bit core, but it's not very fast, because it's still it's just M0 at 32 megahertz. But to this we've got the standard set of peripherals, but not too many, standard set of memories, but not the numbers are not too large, because it's just 8 kilobyte flash memory, 2 kilobyte SRAM, 1 kilobyte EEPROM, plus some basic boot ROM for uploading the software for UART or SPI. Just take a look, just 8 kilobyte flash memory. This is possible, of course, because we've got 16-bit instructions. Don't forget that it's Cortex M0 Plus with TAMP2 instruction set, but Cortex M0 has almost only 16-bit instruction. 32-bit instructions start with Cortex M3 core, which means that 8 kilobyte flash memory is roughly about 4,000 of lines of 4,000 of instructions. This is more than Tiny or PIC10, so you can do something. Not too much. 3 on the other side, 2 kilobytes of SRAM means just because 2 kilobytes, but it's a 32-bit core with 32-bit data being processed, which means that it's 500 cells that you can use, because 2 kilobytes by 4 is 500 cells. Nah, that's actually not too much. So this processor is definitely a simple, very simple processor. It's still very simple processor for very basic use, but it's not as simple as the Tinies or PIC10, PIC12, because of the, take a look about the peripherals. So we've got 2 UARTs with supporting IRDA. We've got the basic SPI, SQC, not too many. We've got only 16-bit timers, but still 16-bit timers. Take a look, only 16-bit, so it's a 32-bit core, but only 16-bit timers. Still better than the competitive 8-bit solutions. In case of analog, the comparator, nice thing, temperature sensor, nice bit, but a great advantage over the standard 8-bit solution. So 20-bit, 12-bit ADC SAR with 10 channels and 1 microsecond conversion time. So much faster, so 10 times faster and much more accurate than in case of AVR. In case of the core itself, we've got the memory protection unit you can enable. This is M0 Plus. So in M0, MPU is missing. Here MPU is there, which means that we can try to use the maybe not the RTOS, but we can try to make our software a bit secure, at least a bit. Internally, additionally, we can count of the power regulators, standard setup in this type of cores. We've got the internal RC oscillators, even not oscillator, but oscillators with very low power and standard oscillators. So 38 kilohertz, of course, is for keeping the processor running at the minimum required power. Then we've got also the ultra low power RC oscillator for scaling up and down processors. So this is the family which are to be used in the ultra low power applications. That's why such a variety of ultra low power oscillator ranging in kilohertz usually, but not very fast. Take a look. It's really so you will not get thousands of MIPS out of this processor. No chance for this. Then basic real-time clocking, SIS time, some basic watchdogs, block for CRC checking, simple block, and that's it. And that's it. So very simple processor with almost no peripherals. Comparable to more complex heterogeneous, because simplest heterogeneous are simpler than this one. But in case of if you take more complex heterogeneous, or you take the PIC 16, this is comparable. This is comparable core, so comparable, and that's what you can expect from this kind of ultra low power core. So that there are just a minimum set of peripherals, still 32-bit peripherals mostly, small amount of RAM, and just the basic functionality. On the other side, we have the processors like here the STM32H743, just that I took to give you the example. This is M7 based core, the M7 with 400 megahertz. Or the M7 with 400 megahertz clocking. This is a super scalar core, meaning that we can have out of this theoretically 800 DMIPS and 2000 core marks, because that's the performance of the core. That's the performance of the core itself. We've got on the board the cache as well, so 16 2 times 16 kilobytes, plus the floating point unit, plus of course the memory protection unit as well, plus the DMA, so direct memory access 4 times the DMA, plus a lot of things. Of course, much more memory here you can expect from this kind of processor. So instead of 8 kilobytes in the L0, take a look how much different is there. So we talk here about 2 megabytes of dual bank flash RAM, plus more than plus 1 megabyte of SRAM. 1 megabyte, not this time 2 kilobytes, but 1 megabyte of flash RAM, of SRAM, and plus the support, of course, for many connectivity, various connectivity solutions. So yeah, a lot of interfaces, various kinds. So even in the L0, 1 SPI, 1 I2C here, 6 SPIs, 3 I2Cs, 4 I2Cs, 3 I2Ss, camera interface, Ethernet, MDIO, USB, 2 versions of USB, and so on, so on. The list go really far. But then we have an upgrade path to this. So the multi-core with the A7. So here is the MP1. So that's also something available today, and that's also something that we can use with extensive security this time. With the improved even connectivity, so with even more options, because this processor is even larger, so we have even more memory here. We have even more memory of any kind, because we've got 2 processors, more cache, of course, because instead of 16 plus 16 kilobytes, we've got 32 plus 32 plus 256 kilobytes of the flash of the second level. So more peripherals of any kinds, and more speed, more performance of the processor. So still we are in the microcontroller family. So take a look and compare how large difference is it between this basic L0 core and this core, how many different peripherals we have. So a lot of capabilities in the world of our microcontrollers, and of course there is a whole spectrum in between those 2 cores that you can find on the market and you can adapt. to your needs, especially with the use of the CMSIS, where you can easily, in a pretty simple way, even jump from platform to platform, so that you make one application on Texas Instruments, another application on NXP, another application on ST. It is possible with the use of CMSIS, and that's the conclusion of our today's class. Any questions? Maybe. Okay, if no questions, thank you very much for your attention. See you next time, probably remotely again. Have a nice day then. Bye-bye.
Thank you. Goodbye.